Hello all, today we will see types of segment descriptors and their format. So here is the following figure. We can see these are segment descriptors of two types. One is the system and another is the non-system. Now in when we talk about system descriptors, these we have already having a little bit of description in the previous unit, that are nothing but LDT, gate, TSS. Gate is that what we will see. It is something a bit new uh, to related to these descriptors, but we had seen what is LDT, that is local descriptor table. TSS means task. It is related to all task switching, that is TSS, and gate. Okay. And under the category of non-system, we have code and data. So let's start. The following figure will show the type of segment descriptors. There are two main categories of segments. Basically, that are system segments and non-system segments. So these two basic types are further categorized into 5 types. This is 1, 2, 3, 4, and 5. Next. The non-system, that is code and data segment descriptors. The code and data segment descriptors are the non-system segment descriptors as it is mentioned in the category itself. Then the second point, the following figure shows the general format for code and data segment descriptors, and the table given illustrates how specific bits in the access write byte are interpreted in the data and the code segment descriptors. What is the meaning of these two lines is that this is a format. There are two different formats. Now this point is very important. There are two different general formats. One format is for the data segment descriptor and second is for the executable or code segment descriptors. Code and data are two segment descriptors that fall under the category of non-system segment descriptors. So the generalized format is given over here, and let's start comparing now what is different in these two formats. Overall, mostly the format is same, everything is same, but there are few changes that makes them different from each other. So now let's get started. So the first format, that is figure number A, data segment descriptor. It consists of 0 to 31, that is it is a 32-bit segment descriptor. Fine. First segment limit 0 to 15 is given as the segment limit. Similarly, 0 to 15 is given as the segment base. Now this is in the figure number A. Come to figure number B, that is code segment descriptor. Same, we have 0 to 15 as a segment limit. Even the code segment is a 32-bit segment descriptor. Then 0 to 15, that is we have a 16-bit of the segment limit, and remaining 16-bit is the segment base. Same, these two fields are same. Now come under the category of first 16-bit, that is the segment limit. Now we will see the first part, that is the base. Over here it is also as the base. These descriptions are given below, but just try to figure out how the actual format is. So we are over here first going to see bit by bit the description. Now base 16 to 23, 16 to 23, same. Come to the second field, A is nothing but the access write byte field. It is differentiated. How it is differentiated, we'll see that in the next slide. So this also bit is same. Then come to the type. This is again type. Now over here, see 0, we have 1. Here is E, here is C, here is W, and here is R. So 0 and 1, 0 will denote data segment, 1 will denote the code segment. E is nothing but executable, W is nothing but write, C is nothing but conforming bit, and R is nothing but read. Okay, so we have found our first difference between the format, that is under the category in the type bit. Type bit we have 0 E and W for data segment and 1 C and R for code segment. Then next is 1, over here 1, same. Then the next field is DPL, over here DPL. DPL is nothing but descriptors privilege level. So both fields are same. Then we'll come to the P bit. P bit is nothing but the present bit. So we have covered over here 0 to 15. First 16 bits of the data segment descriptor and the code segment descriptors are slightly different with respect to the type field. Okay. Then come to the next remaining 16 bits over here. Come to the section of segment base. Now in the segment base, we have the limit. Yes, limit, same. AVL, AVL, same. O, O, same. It's 0. Then B and over here D. Now what is the meaning of B? B is nothing but a word called as big. Okay, and D over here denotes default. So here one difference is found in the general format for the descriptors. Then G is nothing but the granularity, and then remaining 24 to 31 is the base again. So what is the difference, students, over here? A very simple to understand is 31-bit segment descriptor is there. One is data, one is code, and the type field are different. Over here in the first 16-bit, the type field is different, and in the remaining 16-bit, the B and the D field is different. So this is nothing but the general format for the data and the code segment descriptors that fall under the category of non-system segment. See over here, non-system segment. This is nothing but the non-system segment, and first category is what? System segments. We will see the description of these bits one by one, what they are telling us. Let's get started. Now I'll show you this slide, but before showing the slide, as I am going to read the bits, you just relate to the figure. I'll just start now reading. We'll relate whatever is the description I am telling you. We will relate this one by one. Now the first thing, B. B is what? Big B bit, that is known as big. What does this B do? The big bit, that is the B bit of the data segment descriptor, determines the size of the stack pointer. See, this bit, it will determine the size of your stack pointer. Okay. So if your B bit is 0, the size is 16 bit, and if your B bit is 1, the size is 32 bit. So when it comes to 32 bit, what is the stack pointer called as? ESP, extended stack pointer. As you know, we are 80386 is a 32-bit microprocessor, and we have the expansion given as E flags, E registers, E AX, EBX, their general purpose registers. So wherever E is added, the meaning of E is ESP, extended stack pointer. Extended means what? It comes under the category of 32 bits. So whenever your this B bit is 0, it will be denoting that it is 16 bit. And whenever this bit is 1, it will denote that the stack pointer is 32 bit. That is extended stack pointer. Same is the case with D bit. It is nothing but the default size. So what does this bit tell? This bit of the code segment. Now D is associated with which segment? It is associated with the code segment. See over here, D is associated with the code segment descriptors. So this bit of code segment descriptor determines the default size of operand. Whatever is your operand, its default size will be determined, and also the default size of address of the instruction. Whatever is the default size of the address for the instruction of a code segment. So that instruction can be any instruction. So what two things the D bit will tell you? Default size of operand and default size of address for the instruction of a code segment. So similarly, when the D bit is 0, its size is 16. When the D bit is 1, its size is 32. Then we'll come to E bit. Let's come to this E bit now. See over here. Under the type field, we have a E bit. What does this E bit tell you? Executable. This bit indicates whether a segment is a code or a data segment. Now, how it will tell? If your E bit is 1, segment is a code segment. Otherwise, segment is a data segment. Very simple. Meaning of E means executable bit. This will tell you whether your segment is a code, sorry, whether it is a code or a data segment. How it will tell? When your e bit is 1, it will tell you it is a, when your bit is 1, it will tell you it is a code segment, and if your e bit is 0, it will tell you that it is a data segment. Then next we'll come to the code segment may be executable. This point is very important. Whatever is your code segment, it may be executable or executable and read. These are two different conditions. Code segment can either be only executable or it can be execute and read. So this is determined with the readable bit, that is the R bit. See, this is the bit, that is the readable bit, this R bit. Who will tell you this? Whenever, just wait, your code segment, see over here. This is nothing but your format of a code segment. This is a code segment format. It will determine this code segment is executable or it is executable and read. Okay, but who will tell you whether it is executable and read? This R bit, this readable bit. Fine. How it is telling? See, it is, if the R bit is 1, code segment is executable, and if your R bit is 0, the code segment is not executable. That much simple. R bit is 1, code segment is executable and readable, and if it is 0, then the code segment is only executable. You cannot do anything with it. Next is the conforming bit. Conforming bit means if it is set to 1, if this bit is set to 1, the code segment can be executed and shared by the programs at different privilege level. This bit is very important because conforming bit will tell you, or it will allow a code segment that it can also execute and share, or it can be also be executed and shared by the programs at different privilege levels. If this bit is 0, if this bit is 0, then it cannot be executed and shared. Fine. This is the case. I'll repeat again. The conforming bit, that is the C bit, if it is 1, then the code segment can be executed and it can be shared by the programs at the different privilege levels. Fine. Then this is a very important figure over here, as it will tell you the maximum limit and the expansion cat type, upward expansion and downward expansion. How it will tell you? See, in case of a stack segment, okay, there is a stack segment. The segment starts at the base linear address plus the maximum segment limit. Come to the stack segment. There are two types of segment, data and stack. Okay, so when you talk about a stack segment, the segment will start at the base address. See, this base address is in the upward direction, or it is at the top, not upward direction. Base address is present at the top and your maximum limit is present at the bottom. So how it is starting? See, segment starts at the base address plus the maximum segment limit. Okay, whereas your data segment, it will start base address and expand to the, and it will expand to the base address limit as shown in the figure. Okay, over here there is one slight correction. I have repeated by mistake. See, your data segment, it will start at the base linear address and expand to the maximum limit. A correction is made over here. Expand to the base address, base linear address. Instead of this word, the word should be maximum limit. Fine. So I repeat again, your stack segment, it will start base address plus the maximum limit in a downward direction, and your data segment will start base linear address plus maximum limit in a upward direction. Fine. So this is the figure shown below. Then the expansion direction, that is the ED bit, it will specify expansion direction for the segment. If there is one bit called as the ed bit, fine. What is the work of this expansion direction bit? It will specify the expansion direction, whether the expansion is in upward direction or whether it is in downward direction. So when this ed bit is 0, your expansion direction is in a upward way, okay, which is related to the data segment. And when your ed bit is 1, the expansion direction is in a downward way, which is related to the stack segment. I repeat over here. Just see over here. Wait a minute. See, when there is a bit called as a ed bit. When this ed bit is 0, so expansion direction is related to the stack segment, that is in the downward direction. And when the ed bit is set to 1, the expansion direction is in the upward direction, that is related to the data segment. It is that simple. Then we'll come to the W, that is the write bit for data segment. In our data segment, there is a write bit. See over here. This W, we are talking about this W now. Okay, that is related to your data segment. So what does this field tell you? The write bit for the data segment, it will indicate whether the data segment is read only or read and write. Okay, these are two conditions. Either it is read only, means you can only read the data, and the second condition is what? The data segment can be read as well as it can be written. So these are two conditions. So who will decide these conditions? The W bit. So when your W bit is 0, data segment is read only. That is first condition. And when your W bit is 1, the data segment can be read as well as it can be written. Fine. So for stack segment, bit must be logic 1. Whenever you talk the about stack segment, the W, that is the write bit, it should always be logic 1. Okay. Then come to the table. We'll see this table now. This is nothing but the just overview of the bits that we have seen now. So P is nothing but your present bit. If the P is 1, this is the bit position. See, come to the table now. First column is nothing but it will tell the bit positions. These are all related to your bit positions. Second column will tell you the name of the bit. Then the third column, it is the bigger column that will tell you the function of these particular bits. Okay, now let's see. P, that is the present bit. When it is 1, the segment is mapped into the physical memory, and when the present bit is 0, no mapping to the physical memory exists, comma, base and limit are not used. This, the meaning means what? That particular segment is 1 means P. When your P bit is 1 means what? That particular segment is present, and when your P bit is 0 means the segment is absent. So no mapping, no base and limit is defined, or we cannot perform any activity. Then come to the DPL, that is the descriptors privilege level. This DPL is present over here. See, now we are talking about this DPL. DPL. Okay, this bit. What does this bit tell us? It is the descriptors privilege level. Segment privilege attributes used in the privilege tests. There are different privilege tests, and the segment privilege attributes are used. Whatever are the attributes related to the segment privileges, they are used in the privilege test. Okay. So next is the segment descriptor, that is S. When this is 1, code or the data segment descriptor. That means it also includes the stack. When you're talking about segment descriptors, it also means code, it also means data, it also means stack. Okay. If it is 0, system segment descriptor or the gate descriptor. Very simple. Segment descriptor, if this bit is 1, then it will be a non-system segment descriptor, and when the bit is 0, S bit is 0, it will come to the category of system segment descriptors, that is LDT, gate, TSS. Then is executable. If E is 0, the descriptor type is the data segment. Okay, and the expansion is in the see ed. If e is 0 means executable, the descriptor type is data segment. It is mentioned in this diagram. See, it is mentioned over here. When your e is 0, when your e is 0, it is the data segment. Fine. And when your ed is 0, expansion direction is 0, expand up of segment offset must be less than or equal to the limit. That means you are talking about data segment. See over here, these all these all fields are related to the data segment. 1, 2, 3, 4, they all are related to the data segment. So it is mentioned in this corner. These all fields are related to data segment. So when E is 0, your descriptor type is data segment. When you are talking about ED 0, that is your expansion is in the upward direction. So, okay. Then it is expand. What you have to expand? The segment offset must be less than the limit. Okay, you're talking about data segment. Then when your ed is 1, that is in the downward direction. When the expansion data is 1, then you are moving in a downward direction. And when your expansion direction is 0, you are moving in a upward direction. That's simple. So the offset, the segment and offset must be greater than 1. 0, I'll tell you a very key point to remember this bit. When your ED is 0, your limit is less. And when your ED is 1, your offset and segment are greater than the limit. And ED 0 means what? Offset and segment are less than the limit. So 0 is less and 1 is greater. Then same is the case with the writable, that is the W bit. When your W bit is 0, the data segment may not be written into. So wherever you have to write the data, so it is given into the data segment. Okay. And when your W bit is 1, the data segment may be written into. This is a bit confusion over here. When you come to this bit, no, when W is set to 0, the data segment may not be written. Means your data segment, you are not allowed to write into the data segment. One writable bit is 0. And when the W bit is 1, the data segment may be written. Means you can have a written access to it. Then come to the next column over here. There is a note given if the data segment S is 1 and E is equals to 0. S is 1 means what? It is segment descriptor, and E means what? Executable. Now same fields E, C and R we are talking about with respect to code segment. I'll show the diagram. See the code segment. E means executable, that is also applied to the data segment over here. Oh, sorry, code segment over here. Similarly, C and similarly R. Now we are talking about these fields in the diagram. Oh, sorry, in the table. So E means executable, C means conforming, R means readable. Whenever your E is 1, descriptor type is code. See, whenever your E was 0, your descriptor type was data. When your C is 1, conforming bit. So code segment may only be executed. It is very important. When the C is 1, your code segment may only be executed. But when it can be executed? When CPL is greater than or equal to DPL and CPL remains unchanged. These are nothing but privilege levels. D is the descriptor's privilege level. So, and C is associated with another type of a privilege level. So, code segment may only be executed when CPL is greater than the DPL and CPL remains unchanged. R is readable. Readable means what? You can only read, but when if R is 0, code segment may not be readable. And when R is 1, code segment may be readable. This you can relate, this R bit you can relate with this W bit. See, data segment is used for the purpose of writing. Code segment is used for the purpose of reading. So when W is 0, data segment cannot be written. When W is 1, data segment can be written. Similarly, when readable, R is 0, code segment cannot be read. When R is 1, code segment can be read. Okay. Now another note is given over here. If the code segment, see how a note was given for data segment, similarly a note is given for the code segment also. If code segment, in the code segment this S bit, that is segment descriptor bit, is 1 and executable bit is 1, then what will happen? The A bit, that is the accessed bit, that is the position number 0. This position number, we are talking about this bit now. See, this is the A bit, accessed bit. Okay. So this bit, if it is 0, segment has not been accessed. This means the segment is yet to be accessed. And if this is 1, if this bit is 1, segment selector has been loaded into the segment register or used by the selector test instruction. A will tell you that whatever is your segment selector, it has been loaded into the segment register and it is ready for use. Okay. And who will use it? It will be used by the selector test instructions. Okay. So after this, the next thing that we'll study are the various types of descriptor tables, IDTR, LDTR, then the table registers. So up till here, I hope you all have understood. This table is just for your knowledge, for your reference, that which bit is doing which functionality, or which bit is, what is the name of the bit, what is its position, and what the functionality is getting carried out. Okay, fine. So thank you.